first, I would like to thank Professor Kim and the college in the KAIST. And they handle a very good organization and hospitality for our Fudan peoples. And today, I will talk about some very simple things. Because we have a long time talks and some you are perhaps tired a little. And I will talk about two things. One is how to represent the functions. The second is how to represent the derivatives. And then we want to use the MQ-quasi interpolation to estimate the derivatives. Okay. Professor Lin has already talked about what is the applied mathematics. The first sentence is to answer the what is the applied mathematics too. Yeah, the applied mathematics is always difficult to define. One said it is applied mathematics, one said it's a mathematical application, and okay, I don't care. But applied maths possess two parts. One is application, and the second is mathematics. What is the interface between the application and the mathematics? Then this is the data. We cannot get functions from application. We can only get data, finite data. And then to the mathematics, we shall from the data to construct some functions, such as Professor Kang's work in finite mathematics. They want to find from the data such data and to find such functions. Yeah, and from Professor Kill's work, they for the classification from such data. And we want to find functions. Okay, if we have a function, if we have a function, what is function? What is this? What is this? For the applied mathematics, we should use some formula to represent them. We cannot say the function is in finite space or anywhere. We should say the function is a polynomial, a trigonometric polynomial, or he used the Gaussian kernel, yeah? And you should use some formula to represent the functions. Then the basic problem is this. We should from the data to find some method to represent in function, and then our mathematician can involve in this work. And we can analyze the function, and we can take the derivatives, and so on. And then is our work. This is the interface, very important part of the applied mathematics. To return a function, we require a function space. For example, the polynomial. For example. However, any finite degree polynomial that cannot represent any function. Any function. We should have a nested space. For example, the polynomial, we should this is the degree of n, and this function space is included in the degree of n plus 1, and so on and so on. Then the space is always larger and larger and larger. Then we can use such nested space to approximate any functions. And if we do the approximation, this is very simple. We require only to take the projection. We only take the projection to the next space, and then we can have a series of functions. The functions are approximated to the target function. To calculate the projection, we require a basis. If we have no basis, we cannot do such things. Beta is also normal basis. If you have no also normal basis, then we can calculate our dual basis and to calculate the approximation. The key feature. What is the basis? The key feature of the basis is using these basic functions to represent or approximate the target or complicated function. Or in other words, the function is or can be constructed by linear combination of the basis. What is basis? That we can define it that it is the smallest set which can be combined to represent the function. I will come back to the physics and the chemistry. What is substance? We ask the physicists.
Physician. Physician is not physicist.
Physician.
Yeah, physician is doctor.
It's okay.
Right.
Yeah.
Physics, yeah. Which one is like?
Physicist.
Physicist.
Yeah, physicist.
Thank you.
Physician is doctor.
Thank you. Substance is controlled by atoms and elements, or linear combined. For example, the water is 2H plus O. It's a linear combination. And the salt is Na plus Cl. It's a linear combination. If you take my person, it's a linear combination of 130 atoms. Yeah? Linear combination. Then we compare the physics and the mathematics. We can say the basis is atoms in mathematics or elements in mathematics. Atoms or elements is the basis of the substance in physics or chemistry. However, we should ask the physicists they say the atoms is controlled by smaller particles. This is a very important problem in mathematics too. If we have polynomials, say, of degree 2, then we have 3 bases. The space is 3-dimensional space. This is okay, no problem. We always use such functions. However, we know the polynomial of degree 2 can do almost nothing. The capacity of the polynomial of degree 2 to represent a function, they can only represent as such way. If we have such function, then you cannot use the polynomial of degree 2 to represent such functions. If you have if you use the function in finance or in biology, then we can face to the multivariate problem. For example, we have 100 variables. What is the 100 variate polynomial of degree 2? Then the basis of such space is 3 power 100. 3 power 100. This means you cannot even store your basis in your computer. And then you cannot represent any function. This means then the physics has already solved this problem. They said that the atoms is constructed by most small things. Then we ask our mathematics if the basis is constructed by most smaller things, most basic things. Is the basis in mathematics constructed by most small things? The answer is yes. For example, polynomial. the linear combination of the shifts of the n power to x power to n will generate the polynomial space of the domain. Only one function. We only make the copy of them. This means shifts, copy, 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 and a linear combination. Then we can construct the polynomial space. Any n plus 1 pairwise distinct shifts is a basis of the space of polynomial space. This is an example. Therefore, this function, x power to n, is a basic function and plays a more basic role in polynomial space. And the polynomial space of degree n is constructed by a linear combination of the shifts of the xn. And then we give a definition. It is used by your talk, generator. Yeah? If in the function space there exists a function gx such that the shifts and the linear combination can generate the function space, then the gx is called the generator of the space. The generator is a basic function of fundamental particles of the function space, which contain all the DNA of the space. Here is some more examples. You can take x power to n, you can take sine nx, you can take ex plus e 2x, or x absolute with the value of the x power to 2k plus 1 and so on. And such functions is really very interesting. The first one generates the polynomial space. This one can generate the trigonometry polynomial space. This one can generate the exponential polynomial space. And this one can generate the polynomial splines. And this one can generate the Chebyshevian splines. And this is Gaussian. Professor here used this kernel too. This is perhaps all the function we learned. We don't know. Perhaps we have a blog, or perhaps we know the technique. Technique is the sine over cosine, yeah. Then we can do the some projection method to get the such function. If you only take the linear combination, then this is perhaps all the function we learn. We don't learn a lot of other functions. To find the fundamental particles is the basic problem in the physics, and then to find out the generator is the basic problem in function representation too. We find that if more than plus 1 shifts of x power to n is linear dependent, this means such generator can generate only n plus 1 dimensional function space. And we can go in closely in details, and we find that the function which only generates the finite remaining space must be a solution of linear ordinary differential equation with constant coefficients. Now, for the multivariate situation, the condition is necessary but not sufficient. Okay, then we will investigate the linear ordinary differential equation. We can find that this linear differential equation, the solution space is polynomial. This is a trigonometric polynomial. It's exponential polynomial. And they are more complicated. It's algebra of the above functions. And this is a common ordinary differential equation. Then we can solve its characteristic function if this function possesses a lot of lambda j, then the exp lambda jx is a basis, and this function is a generator of the solution space of this ordinary differential equations, solution space of this of the ordinary differential equations. Then such generator contain almost all the functions which we learned. I have already said that using rational form, we can get more as a function space. For solution space, if the solution satisfies this condition, then this is a generator, and we can call it as a standard generator of a solution space. The function g is the first the coefficient of the interpolated polynomial, then the value at lambda j is e power to lambda jx, which we can write in this way. This can be explicitly represented as exponential functions, the linear combination of this one. The approximation capacity is limited if the generator can only generate a finite dimensional space. We require always a list space. The space should be large and large and contain all the functions. So one method to generate an infinitely dimensional space is by using scales. For example, the polynomial will generate the polynomial will generate the same finite dimensional space by using shifts and scales. However, any non-polynomial generator by using shifts and scales will certainly generate infinite dimensional space and can approximate almost all functions. However, here is the open problem that the algorithm has been asked. Conditions that the generator can generate almost all the function descents for the shifts and the scale if the Fourier transform is not equal to 0 and at least on some interval. And if we take only shifts, the condition is that the Fourier transform is not equal to 0 almost everywhere. How can we construct a new generator based on the standard generator of the solution space of the ordinary differential equations, such that it can generate an infinitely dimensional space and can approximate almost all the functions? This time I asked the biologist. In the biologist, they have a concept, it's called the biomultiformity. And this is the reason a new space appears. And it will be happening via gene mutation. Then we take the gene mutation. If we have a X, this generator is not so good. The shifts of X can only generate a two-dimensional space. This is polynomial of degree 1. However, we take a gene mutation at 0. The X is so, and in the 0 point we take so. Then, based on the generator, we can construct the Euclidean head function. If we take this function as the generator, then we can take the shifts and the linear combination, we can have this one. And this is called the Euclidean head. And this function is very good. The linear combination of this one is a piecewise linear interpolation, and then we know any function can be approximated by the piecewise linear combination. The interpolation is very simple. And then we generated this idea that any standard generator with gene mutation says that only in the 0 point and it goes in opposite side. So we will generate an infinite dimensional space And this is a Chebyshev spline or piecewise function of algebra of all polynomial, triangle, non-trivial polynomial, and exponential polynomial. And it can approximate almost any function. Then I will introduce a more simple generator. This is called radial generator. We take a univariate function, and then we use the Euclidean norm to the x and apply the phi on this one, and get a multivariate function. And then this space, the shifts of capital Phi, is called the radial basis space. Phi x is not necessary to be radial. If the phi is radial, then it's simple. However, the phi is not necessary to be radial. For example, his talk was in his talk like KXXJ. Yeah, if the kernel is like KX minus XJ, then it's a small simple. And if you write the KX minus XJ and apply the Euclidean norms, then it's for example Gaussian kernel. We can construct a dual basis for giving here the surface norm. We can design measurements or norms to form an orthogonal basis for this space. And we require only to using the concept of the reproducing kernel heap space. Conversely, if the space possesses a scheme to compute the inner product, the corresponding reproducing kernel or generator can be computed too. Okay, then I will introduce a spatial generator. Then it's very simple. It's called the multi-quadratic kernel. The representation is very simple. It's c squared plus x squared and get the root. The multi-quadratic function was firstly proposed by Hardy in 1968, which was used for Boeing aircraft design. The multi-quadratic basis is defined as follows. The Hardy showed a lot of applications of multi-quadratic functions in his survey paper. From 1968 to 1988, the multi-quadratic method mostly means the multi-quadratic interpolation. A lot of people is working on these topics. For example, Professor Jung has proved the LP approximation by using multi-quadratics. The multi-quadratic method is a most favorite method. Multi-quadratic method was rated as one of the best methods among 29 scale data interpolation schemes based on their accuracy, stability, efficiency, and memory requirement, and easy to implementation. However, there were only numeric tests and not theory. The interpolation requires to solve a linear system of equations. And I will ask us, can we save the step for solving linear system of equations? The answer is again yes. We use the quasi-interpolation. We do not use the interpolation, however, we use the quasi-interpolation. The quasi-interpolation, for example, we know the Bernstein quasi-interpolation. And the spline and the Shannon sampling in signal process, which Professor Kwong has shown in his talk. And this is for the band limit function. And the Bernstein, B-spans, and the sinc function are some pre-given functions. They get the solution directly and do not require to solve any linear system of equation. And then we can use the MQ kernels to construct a quasi-interpolation. This quasi-interpolation was suggested by Beaton and Paul. they construct three schemes of MQ-quasi interpolation. And this technique is used and applied in the 11 Oscar Awards movie, The Lord of the Rings. And myself and the Schabach generalize the Beaton and Powell result and construct MQ-quasi interpolation and show it is sharp preserving and constantly reproducing and give the error estimates theoretically. And Beaton and Dean gave the theoretical discussion on the MQ-quasi interpolation too. And then some other works, a lot of works to get the further results. And Benny Hong and myself used the cross-interpolation to the numeric solution of the PDEs. For example, the cracks of the boundary testing, the boundary layer problem, and so on. And myself and my former students applied the MQ-quasi to nonlinear PDEs such as Burger's equation and so on. That's the sine-Gordon equation. This is an example for the Burger's equation. And we used the MQ-quasi interpolation to simulate the shock waves. And this is the two pictures together. You cannot make difference. One is for the standard solver with a very small viscosity. And we have directed to solve this problem. Okay. And then we come back to the Schoenberg's model. This cross-interpolation, its less work is shift invalid space, Professor Collins, and expert too. And the scheme is a conservation of order K, if and only if the strength fixed condition is satisfied. They said that if the Fourier transform of phi should satisfy these conditions. The strength fixed conditions are still valid for multivariate problem too. We're using TensorPro. And myself generalized the strength fixed condition to asymptotical strength fixed condition and construct a new quasi-interpolation model as this one, and this can be used for the this can be used for the scale data. For the scale data. Then this is multiple interpolation schemes.
Ten minutes.
10 minutes. Okay, then I will skip. Yeah, okay. And this error is usually happen in the approximation theory. If you have an approximation, say that so we can only get n minus k. And for the MQ-quasi interpolation, the people get this results. This is get by myself. The MQ-quasi interpolation, the error estimate is of order 2. And this is by Duma and Paul, and the derivatives is big O h on h. It is very as usual results as usual. Then the people say then the people believe that the signal of the derivative will not converge in this situation. Recently, we have take a close investigation to the schemes. Then we get this result. This means the KAIST derivatives is still converging. However, in lower convergence order, this is h pod 2 over k plus 1. We compare to this one. If k is equal to 0 is 2 and k equal to 1 is h, is 1. K is equal to 0 is 2, k equal to 1 is 1, and k equal to 2. It is convergent. It is h power to 2 over 3. And it's very good. It's very good. If we take such schemes in PDEs, we do not want to have a very good approximation for the function, but bad in its derivatives. We shall take almost the same approximations for the function and for the derivatives. This is not important. Okay, then we want to discuss the random error to the approximation. If we take the data with a random error, and the error is a white noise, then we come back to the divide difference. We don't know very more about the derivative estimation. Perhaps the people always use the divide difference. So when we take this random error to divide difference, we get the divide difference can be right in this one, and then we can get, if we use the divide difference, then the error of the nth derivatives is smaller than the h power to 2. This is theoretically error estimate. However, if you put the random error in the data, then you get this one. This means you take a derivatives, then you should take you should have a 2n in the nano, where d is the dividance of that. Then if h is very small, then this term is very large, very large. For example, if you use one solid point in 0, 1 intervals, then the h is 1 over solid, and 1 over solid and the power to 2n it's very large. However, if we this is asked that the random error should be smaller than the bigger O h power to 2n plus 2. This means that if we use a 46-bit compute, the compute consists only about 20 significant decimal digits. Then we can only use the divide difference of all the 5 to h is equal to 10 to the power minus 2. And the result is valid only for 2 decimal digits. And if you take the high values of small h, then the result cannot be believed or is not valid. Okay, then we use the MQ-quasi interpolation to estimate the derivatives. We can get this formula. And then we require the random error is smaller than big O h. Here is for the dividance 2n, and now is n over 2. It's a very good success. The random error of the data for the divided ones should be very small and smaller than our 4 hours. Okay, this is not important. This is the results. This is for the second order derivatives, I think, and use 100 points in the 0, 1 intervals. And this is used the divided ones, and this is used MQ-quasi interpolations. Here is the 0.03, and here is 0.002. And the amplitudes is more than the dividance. And on the other hand, the frequency is better too. The frequency for the dividance is large, and with the MQ-quasi would be small. This means the amplitude and the frequency are all improved. Yeah, as from the figure, the MQ-quasi, the MQ-quasi interpolation possesses lower frequency and smaller amplitude of the L oscillation and the dividance. Here is some remarks. The total error of the approximation to some given partial differential equation is, I already said, we want an approximation scheme that the approximate order for the function and the derivative is almost the same. Almost the same. That's not important. Here's references. Thank you for your attention.
Any questions, comments?